Hello, everybody. We will go ahead and get started with the webinar. We're really appreciative that you all could spend some time with us to continue our series in the Pigment 101 webinar series. Today, we're going to talk about pigment characterization and how that can lead us to the performance of the pigments in different application areas. All of this is in an effort to help you to select the best product and pigment chemistry for your application needs. So we will be recording this webinar, and all of those in attendance will get the link to the recording as well as the PDF of the presentation. If you have any questions along the way, feel free to put them in the chat box and I'll address them at the end. So with that, we'll go ahead and get started with the webinar. We are, talking about color. So color is important to everybody's business. Whether you are a manufacturer like Sudarshan or the purchaser of pigments, or the final end customer, or someone who is buying something off the shelf or off the lot. Color is all part of that business, and is there to help make each of our businesses successful. So it's important to understand how the color impacts your business. Color helps us to attract the attention of the end product. It can inspire confidence. It's also a great tool for brand recognition. But the important thing is color is a factor in all of those types of questions as we ponder our business plans and to be able to develop the products that we develop. There are many studies out there about color and how people make decisions, and a number of studies show that a great proportion, almost 3/4 of the buying public, makes that decision right at the shelf. So it's important to make sure that we develop colors that, in a crowded space, can attract the attention of the end buyer. So when you are taking a look at objects, you can shift the purpose of that particular object just by changing the color in there. So because we as humans, we react color intellectually. For example, we cross the street on a green light, but we wait for the red light. But in some cases, and even more importantly, we react to colors emotionally. For example, red is perceived as a more of a warm color, giving way to energy and joy, passion, etc. Blue, on the other hand, is typically perceived as a more colder color. We think of ice and snow and maybe some more colder emotions in there. And so there's lots of color theory and understanding about color, what they can bring to your product and what they can also distract from your product. So there's always some positive and negatives about what that color will give certain aspects of to the end customer in there. So a couple of examples of the red blue here, as to how they appear to the viewer of that particular color. So as Pigments talked about, we always talk about the color indexes. That tells us a whole lot about the chemistry and the color space for each of these areas. The color index is meant to help in that in area. So the first digit in the CI number is always going to tell us whether it's a pigment or a dye of some type. The next one tells us the color space that it falls into. And then the last number itself is really just assigned sequentially at the time that they were developed. and added to the listing. There's always going to be some gaps as pigments become more obsolete or they're actually removed from the list. So that tells us a little bit more about the color space that they're in, and also a little bit more about the chemistry. So when we talk about colorants, we mentioned pigments and dyes. Um, Key differences between the two do have to be understood. And primarily, it really comes down to pigments are physical particles. They will not fully dissolve. They will not dissolve in the medium, whereas the dyes will dissolve. Both can be inorganic or organic in nature, but the key here is that whether or not they dissolve in the medium. And from a property perspective, pigments also get their properties from both the chemistry, and then the finishing techniques will shift the chemistry in the performance in one direction or another. For dyes, 100% of the performance is just the chemistry. And sort of the nomenclature is, if you make a dye insoluble, then you create that pigment. When comparing pigments, we have organic and inorganic. There's a whole host of differences between the two. Both have very important places in color formulation in all application areas. So they have properties that provide the needed end properties for the final formulation. So they're often used together to capture the benefits that each bring and to be able to get to there. But primarily, it really comes down to the shade, where you get much more of a larger color portfolio out of organic pigments, and the color itself is much more brilliant versus inorganic pigments. But inorganic pigments bring a lot of the hiding and opacity that might be required. They are definitely high performance just by their nature. So they can withstand exterior weatherability and very high heat temperatures in there. So this is why I say they both are typically used in conjunction with each other to bring the best properties to the final formulation. So with respect to colorants, they are the properties. We've talked about this many times, that they're governed by the chemical structure in there. That structure then is all starts from the actual crystal structure, and then there's some amount of finishing that's taken place to make that final application area to be able to fit in each of the areas that it's required to fit. Some aspects that govern the performance that you might see, and in this case, color is also a performance property as we go through the discussion. So crystal shape is one area that is very important when it comes to the performance. The shape itself can dictate how easy or difficult it might be to disperse, how much dispersant it might need to fully disperse, as well as some other opacity, as well as some other properties in here. So these are some things to consider. The crystal shape is going to be dictated by the chemistry and the synthesis process that's created. Once it's created, then it can be modified through finishing. Another area that's important to consider is polymorphism. This is where the same chemistry is in the crystal. The crystal is just modified to be able to create the individual products. So the chemistries all look the same, but the structure itself looks different. Two good examples are the CPC blues. So the alpha blues we've talked about this in previous webinars, where they have a wider overlap between the copper atoms in the molecule, causing that more red shade. In the beta blues, the 15-3s and the 15-4s, they have a larger spacing between the shift spacing between the copper atoms in the molecule, giving that more green color positioning of the beta blues. The other classic one is violet 19. Here we have the gamma, which is the red shade version. In this particular case, we have 4 molecules attached to a 5th one, and that results in that more red shade version. And then the beta is the more violet, purple, blue shade, if you will. In this case, it's 2 molecules that are attached to that 3rd one. And those chemically, they are 100% identical. It's just in the structure of that crystal that gives the color spaces of these 2 types of violet 19s. So if we cut to the chase, we always like to say that it's when you create that synthesis of a pigment, you can guarantee certain properties. But that's only available, able to get to that endpoint with some limitations in there. And so some of the things that we'll talk about in this webinar will be examples of some of those limitations in there. But there's always a good amount of information and progress that we can make to get to those endpoints. So when we're talking about color, there's a couple of ways to think about color. And we're all humans, so from the scientific point of view, it's all about the electrons and the light absorbing and reflecting at certain frequencies within the visible light region in there. So a whole host of science is directed at the ways to evaluate color. But we're all humans, as I mentioned, and we all are a little bit different. So in reality, colors don't exist until we actually see them in there. So without the eyes and the brains, there is no color. Sort of similar to the phrase is, if you're in the forest, if a tree falls in the forest, do you hear it? Well, no, you don't hear it because you're not there. Same idea here. If you don't see it, there is no such thing as color. So it's a little bit more of a different way of looking at it. It's more of a neurological phenomenon. And since we're all human, we're all a little bit different. Each of our brains processes that information a little differently. That is why when you put one color on an object, you might look at it and react differently versus another color on that same object. So from the human side as well as from the science side are different ways to consider color. Of course, yeah, it's always nice to be able to express it numerically. That's why we have the color system that we use in a lot of different areas. You can see some examples of 2 roses, a yellow rose and a red rose, and how the color values of those allow us to visualize internally what the color is based on the numerical differences in there. On a chart, here's how another way to take a look at them can be very different in terms of how much redness is there and how much yellowness is there. So you don't necessarily always think about a yellow having a red value or even a red having a yellow value in here, but they do. One thing to always consider, and something that might also cause problems in our everyday work, is metamerism. Here, this is where the color of an object really depends on what type of lighting that the object is being viewed at. So as my little cartoon here shows, you can make a color match indoors and everything is a-okay, but you take those two panels outside in the sunlight and all of a sudden they look like two totally different colors. And so this can really put a bind in your color matching area. And primarily, um, you're not going to have a problem with metamerism if you're staying in the same color indexes that you're used to using. But it can be an issue when you have to go outside of a chemistry to be able to match the color for whatever reason, whether or not you don't have the chemistry in your formulation portfolio, or that chemistry goes away for some reason. Those are the things that all of a sudden we'd start to need to consider metamerism in that type of formulation. A very good example that I keep with me 100% of the time from my early days is when the bismuth vanadate came on the scene a number of years ago, and pigment yellow 151, which is in the same color space, what tended to be replaced by pigment yellow 184, the bismuth vanadate. And everything was okay except for when you went into a green color. This was a huge metamerism impact in there, and there's no way to get around it unless you go back to the original pigment yellow 151, or you just accept the fact and change your color standard in there. So that is one that's always stuck with me over the years in there, but something to consider as we go along. Again, if we go back to what we're really all about here, we do know with respect to color that it's a fact of the chromophores that are apparent in double bonds of the crystal, whether or not there are electron and donor and acceptors present in there. And of course, as I earlier showed you, what is the orientation within the crystal? All of those factors, however, if they are present in the crystal and how much they're present, will provide that ultimate hue. So if we take a look at some different chemistry areas to understand how the hue is impacted by the chemistry itself. So azos is one of the biggest volume colorant chemistry types that are being used in all application areas. So it's a big one to understand. And primarily the basic hue, it comes from the choice of the coupling compound in the manufacturing of these. And then if it's also a laked azo, the salt choice is important for that color space. In there, azos range in a variety of color spaces from yellow all the way through to blues, browns, and violets and browns. As I mentioned, the finishing techniques that are there, they are ways to shift the physical characteristics of that particular chemistry in there. So once you have the basic chemistry, then you can make those shifts in hue based on the choices of finishing that are used. So I mentioned about the choice of the coupling compounds. So here are some monoazo pigments, and the choices of the coupling compound in each of these chemistries do ultimately relate in the actual hue in there. So you can see that the choice of that compound makes the pigment yellow 1 being a pretty green shade all the way through the pigment yellow 65 being a very red shade. I mentioned the salt choice for laked azos, and we talked about this in our last webinar for the pigment red 48, 1, 2, 3, and 4. So that choice of salt that's used to make the laked azo definitely changes the actual hue of that particular one. The physical chemistry is all the same, just the salt choice is different. I already spoke about the polymorphism of the CPC blues. This is just a little bit of a data example of what that space is. So you've got the 15-1 and 15-2s being the alpha blues, the red shade blues. And this is a 50-50 deep tint tone formulation in a powder coating formulation. So you can see on um, the 15-1 and 15-2s being much more on the red side versus the beta blues being on the green side. That finishing technique that I talked about being something that can shift the hue. This is a very good example of that as well for the 15-2, 15-4, which are have a different finishing techniques. You can see how they're shifted to the greener side of each of its sister uh, compounds. And then we again going back to the violet 19s and the two modifications there. You go from a very clean red to a more violet shade based on that modification. So another way to change the color, sticking with the quinaquinones, is doing substitutions, and the choice of the type of substitution and the position of that substitution can very much change the hue of the pigment. So here is the basic quinacridone molecule, the crystal structure that is created. The violet 19s are considered unsubstituted, so there is nothing on the R2, R4, R9, and R11 spaces in there, and this is where you get the two different formulations based on that polymorphism. Now, if you change you start substituting in those positions, the choice of the substitution type as well as the positioning very much changes that color, that hue positioning. So if we go from the unsubstituted violet 19 to the substituted violet or red 122 with a methanol on the 2 here, and the 2 and the 9 spot here with a methyl component in there, we get that very blue shade, pink, magenta shade in there. If we stick with the R2 and the R9 substitution, but change that to a chlorine to get the red 202, we go to a very red positioning for a hue. And then sticking with the chlorine substitution, but we move to the 4 and the 11 spot, we get the red 209, which then goes to a bluer shade red positioning. On the inorganic, you also can change the color by changing the type of substitution used. Here we have 3 examples of a rutile CICPs. And so compositionally, they're very similar, just the base metal is different, going from nickel, providing a yellow positioning, chromium giving a more buff or a tan positioning, and the manganese giving that brown color space. So there are many things to consider, and this these are all examples of how the design of the molecule can impact the actual hue of that end product. Tint strength is another colorant color definition that we use. There are many ways to define it, but really we want to understand how much light is how much is light is absorbed and by the crystal, and that is usually done when mixed with a TiO2 to be able to understand how much reflection and absorption is taking place. There are a lot of different ways to define it and talk about it in terms of communication. You can use just an absolute value. A lot of times you'll hear me talk about the tint tone L value in there. So it's a way to talk about the individual pigment itself. It can also be relative to another pigment or another product in the same category. So you'll have a relative strength in there when you want to compare it to something. Another area is that is used in the industry is talking about the standard depth. And here we want to is another way, and another absolute way to compare one pigment to another. And we define this as the amount of TiO2 that's needed to move 1 gram of the pigment to reach a certain defined depth. And typically it's 1/3 depth in here. So a number of different ways to communicate strength depending on what you're using it for. So if we talk about ways to increase strength within chemistries, going back to the chemistries that we've talked about before for hue, in the azo chemistry, if we move from a monoazo to a disazo, essentially doubling that azo component in the structure, we start to see some increases in strength here. So for a monoazo, this pigment yellow pigment yellow 3, I should say, on the green side, it requires 2 grams of TiO2 to get to that 1/3 depth. If you go over to the similar color position, disazo pigment, it requires 3 grams of TiO2 to get to that standard position. So we see some improvements there by doubling that azo component. In quinacridone, we talked about the substitute type and position in the hue, but it also shows up as a function of the strength as well. Sticking with the 2 different types of unsubstituted violet 19s, where there's no substitution on there, anywhere from 4 to 6 grams of TiO2 to get to standard depth, depending on which modification you're looking at. If we go to the actual substitutions and the type and position, if we compare the 122 to the red 202, here the positioning is the same. It's just the molecule or the substitution that's very different. So we lose a little bit of strength with respect to the chlorine on the 202. And then if we change that chlorine positioning to get to the 209, we see some further strength reduction to get for the pigment red to 209 at 3 grams of TiO2 versus the 4.5 grams of TiO2 for pigment red 202. So again, the design of the chemistry is a very impactful on the strength. From a sort of a performance aspect of it, light fastness and weather fastness is always key in all parts of the color industry. and depending on what your end requirements needs, these are two properties that have to be taken in consideration when you're selecting your pigment choice for that one. Primarily, these are chemistry-driven properties. Um, it's a little bit more difficult to correlate the chemistry in a very clear relationship to the light fastness and weather fastness. But we do have data to suggest that there is a good response there as well. The other thing to consider is the surrounding medium will definitely impact that. So when we do the comparisons and testing of these, that medium is always the same because we want to be able to remove that aspect from the testing results so that we can focus on the pigment itself. However, that's not 100% effective because the finishing that might be used can also interact with the medium itself. So if you're looking at a variety of products in one color index in the same formulation, you can still have a little bit of a difference in the response because there might be some interaction between that and the medium. So there's a lot of things to consider. We do try to make those correlations in to the from the chemistry to the response. But before I go to a couple of examples, let me give you a little bit of background on each of these as well so that you have an understanding of what's done. So light fastness, if you take a look at a typical COA or technical data sheet of pigments, you'll see something that's in reference to a blue wall scale. This is a industry standard method for identifying the light fastness properties. It will be a rating between 0 and 8, with 8 being no change. And here it is an accelerated process for measurement, but we try to develop the equivalent of exposure to sunlight for a 3-month period for this particular testing. So some examples of what the numbers translate to in terms of, say, delta E in here. So if you're seeing a rating of an 8 on the blue wall scale, that translates roughly to less than 1 delta E for that light fastness. And then you can see down the line in the chart what the delta E approximate equivalent for that rating scale to be able to do that. And another example on the right-hand side gives a little bit more definition to the rating scale so that it helps to dial in to the selection process. Weather fastness also uses a scale. It's called the gray scale. Very similar in terms of the approach. Here it's a scale of 1 to 5, with 5 being the best in here. But it also incorporates both the visible light, UV radiation, IR, as well as weather conditions, so humidity, rain, all in an effort to mimic a real life environment in terms of this area. So this is also going to be an accelerated area, but to be able to simulate what the outdoor exposure would look like. Again, it's also related to the medium that is being used. And in this particular case, it's also the medium is a little bit more of a factor here as well. So we'd be able to have to do that. In that 1 to 5 rating, you have the color shift as being a majority part of it, but also changes in any kind of gloss, any kind of chalking that might occur is also part of that rating scale. So like the blue wool scale, there's a rating difference that a visual chart is used to select it. Oftentimes you might actually get a half unit in the rating scale in there. So on the light fastness scale, you'll sometimes see a 2 number, a 7, 8 kind of a thing where it is put in the middle of the two spaces. On the grayscale, you'll actually see a half unit step change in the data response. So it provides 9 possible values versus just the 5. So from a chemistry perspective, what impacts? So we go back to the azos in there, and so when we talk about the light fastness and weather fastness, we have to consider the electron acceptors introduced through the first part, the amine part of it is the first step in the process. The coupling agent is a second step. So those two will help to define what that response is going to be. And in the other thing to consider is on the disazo, that one that has the 2 azo groups, there's less of the impact from the amine and more so of the coupling agent selection in there, because now you have 2 coupling agents on either end of the crystal. Laking is a third aspect of performance if it is a laked azo in there. So if we take a look at some of the same types of chemistries and their impact, here is the light fastness and weather fastness for monoazos, the same ones that we looked at earlier. And the chart that I have here on the left is the light fastness and weather fastness for each of these chemistries. So as I mentioned in the earlier slide, the choice of the amine as well as the choice of the coupling agent does directly impact the response in these fastness areas. So we can see especially in the weather fastness for these monoazos, the selection that provides the redder shade yellow 74s and yellow 65s also helps to bring some amount of weather fastness to these monoazos, where the choice here with the pigment yellow 1 and the pigment yellow 3 really does keep them away from being used for exterior. When we shift over to the disazo, again, we have 2 of the azo bonds in the crystal, with 2 of the coupling agents on either end for that aspect of it. Same idea here. The light fastness tends to change depending on what that selection is. In this case, weather fastness is not improved because primarily, if we look back, I mentioned that there's less of the amine that is part of this chemistry, so the weather fastness is impacted by that function. Laking, we talked about this in the earlier webinar, and this chart came from that one. So we talked about where the salt metal is located on the periodic chart, and we see that the pigment red 2 and 4, which are on that 4th row, do have a slight advantage in terms of light fastness versus the other two in here, although all of them are not appropriate for exteriors. And then shifting over to the quinacridones, here it's really the positioning, the choice of the pattern, as well as the positioning of the um, substitution that makes a big difference. Primarily, this comes from the distance between the substitution part and the NH positioning here. So the closer the substitution is to these NH, the poorer the response in these areas. So if we go down here and take a look at the light fastness and weather fastness data, uh, the um, the substitution for the red 122 doesn't change at all from the violet 19 unsubstituted. So the methyl substitution does not deteriorate from the lighter weather fastness aspect of it. When you switch over to the chlorine from the methyl, to create the pigment red 202, we start to see some differences in the weather fastness um, in for the red 122, and then switching the positioning of that chlorine to get to the pigment red 209, we see additional light fastness start to creep in, as well as the weather fastness. Again, it's because here the closeness to those nitrogen NH parts is very close. Solvent and migration fastness is a key property in a number of application areas, and needs to be understood from how the chemistry is a function of this. And in this particular case, again, the chemistry itself is the primary uh, part of the actual performance area. Although the medium itself also does play a role in there. So the two do have to be paired up, and I have an example of that in the next couple of slides. And there's ways to improve this that I have examples for as well for that one. But going back to the medium, here's an example of a violet 23 bleed test in two different types of polymers. In this particular case, these two examples of violet 23, a blue shade and a red shade, they have very good bleeding results in the LDPE. But once we switch over to a PVC and we test the same bleeding response, one product, the blue shade, has a poorer response than the red shade version in there. So the finishing that is used for these two types of violet 23s, again, the chemistry is the same, it's just the finishing that's different, does impact that based on the medium that it's put in. One again, going to the azo chemistries, going from a mono to a disazo is another way to change the response for bleeding. It's a little fuzzy here, little more fuzzy here because there's so many aspects of it. But what I put in here are the bleeding results, an average of over 5 solvents that these are tested in. So some are going to be better than others. So I just did an average over the 5. And then from the mono to the di, I did an average over all of these in here. So if we look on average, the going from a monoazo to a disazo, the bleeding is a little bit improved. But from a similar chemistry perspective, we start to see some differences between the mono and the disazo in each of these areas. Um, when we another area is that's really key in terms of minimizing the amount of bleeding. We want to be able to have as much insoluble substitutes that are on the crystal as possible to be able to keep it from going to the other going bleeding through to the medium in here. And so these are some examples of changing that, providing some more insoluble parts to the crystal. So if we take a look at four different red pigments and take a look at the number of these um, additives on the ring, we can see some changes in the results. So if we start with a red 3, with a bleeding, again, averaging over 5 solvents, is a little bit less than 3. We move to a pigment red 13, and we start to see one of these additives on there having a bleeding of 4. When we go to 2 of those on the crystal with pigment red 170, we again see an improvement overall, and then all the way to a very good rating of a 5 when there are 3 of those on the crystal structure with pigment red 187. So just another way to potentially improve that property for a color space. And then lastly, if we take a look at laked pigments, there are ways to make that improvement as well. So here is the pigment red 48.4 and a pigment red 48 or 53.1, and increasing the bleeding response can be done by having more of the sulfur groups present in the crystal structure that is in there. So in this particular case, the red 53.1 has 2 of those versus the 1 in the pigment red 48.4, and we see an improvement in the bleeding response. So different ways to improve that property. And we talked in for the quinacridones, the position of the substitutes. The same is true for azos as well. So in this particular case, the positioning of one of the substitutes on the aromatic ring dictates what the response in bleeding will be. So here we start with a red 2, and there is no substitutes on that particular ring. So we start out with a bleeding of 2.6. Moving over to the red 112, where we start to have 1, and this particular positioning on that ring actually detracts away from bleeding in that particular case. Red 5, where the positioning changes, improves the bleed. Red 146, again, with the positioning change, is about the same in terms of overall average bleed resistance. And then red 170, again, the positioning and the type is a little bit different in there with a better response for that one. So in this particular case, there's a lot of ways to change the um, the 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 response for the technical properties in here. So these are just some examples of the actual pigment chemistry and its characterization, and how we can attribute that characterization to the performance. There was a lot more that I could have brought in here, but I wanted to make sure that I respected all of your time and be able to keep it within the structure that I've set up. So I'll stop here. and begin to open it up for questions as well. But I did want to, of course, remind you that the team here is here to help you. So you can reach out to any one of us to for any kind of question that you have or any assistance that we might be able to give you. So our next webinar will be in August. We're going to take July off. It's a big holiday month, so I want to be able to make sure that everybody has an enjoyable summer here. So we'll take a look in August at a closer look to some blues, the CPC blues space, kind of similar to what we did with the Pigment Red 48, where we're going to take a look at it in all application areas. That'll be the last Tuesday of the month in August. That will be August 27th. And then September is a big technical conference month for us. So we will take September off and come back at it in October. That subject is still to be determined, so you can hold out for that one, and we'll pick it up again in October. I'd like to thank you again for joining us. We really appreciate you taking the time, and at this point, I'd like to open it up.